Hello student, welcome to our class Mechanics of Materials. This is the last lectures of this semester, and today in today's lectures I'm going to discuss buckling of columns. So there are two terms actually here, one is buckling and column. So let's first talk about the columns. So remember in the previous class says when I discussed about the beam, so I said the beam, if you remember, beam is a long slender member which is supported either one end or two end, and the beam is subject to shear stress and bending. Beam is subject to bending. It is if this beam is oriented like that, and you applied load on the top of it, then this is known as column. Okay. Now the definition of column is columns are slender member subjected to a axial compressive force. Now if I apply load from the top, and because of this load it compressed this column, then now we can tell this structure a column. Now this is not a column. If you pull this member, then this is not a column. So to be a column, the criteria it needs to be meet is it should be in compressive force. The force should be compressive. Now when you apply load in a column, okay, when we apply load in a column, say this is a column, this is P, and when I apply load here, say this load is, and there is a possibility this column can buckle. This column can buckle. That means basically, what does that mean? The buckling actually is we call this lateral deflection. You see this lateral deflection of column is known as buckling. Okay, now so let me give you one example. So here in this particular example, this is a column which is a support at the bottom, and you applied load, and because of this load, this column actually there's a lateral deflection, the buckling occurs. As you see, this steel column basically bent in a lateral direction, and this is also bent. So because what happens is the structure gets weak, or some reasons that its load, this load actually more than a particular value which is called critical value. I will discuss the critical value later, and as a result it gets buckled. And so the another example is buckle can be occurred due to both of the axial load and the horizontal load. Okay, for example, if you apply load from the top and then apply lateral force, then it can create a buckle, even though if so there is a dual action of forces from the top and from the lateral direction, you may cause buckle. So this is an example of an oil offshore platform. As you see, this platform actually collapsed because of the wind of a hurricane. Actually, wind of hurricane acts as in lateral force, and because of this lateral force and in addition of this axial compressive load, this platform, as you see this here, this column actually buckle. So this is a very common phenomenon, common occurrence in the structural engineering. Now, so as I said, this buckle can be occurred due to the axial compression load, and also by combination of axial load and lateral force. Now, so what happens? So say you apply a compressive load in a column. Okay, and this is P1 and this is P2. Now, so you increase the load, and let's say okay, so let's say these let me draw it again. Actually, I think I can draw it again, it's better. So you have a column, it is P1, and then what happened, you have, because of this compressive load, this green line is your new position of the column, so it compressed, so its height reduces but it increases the lateral dimension. Okay, so it compressed. Then so here P1 is greater than P2. Now if we increase the load further at certain point, now what you're gonna see, that you'll start see that your column started to bend. Okay, your column started to bend, and the load at which your column started to bend is known as P critical. Okay, so the critical load, at critical load, P critical, the column starts buckling, and it is very important to know this critical load for the design of the columns. So there is a formula. I'm not going to derive this formula, but I'm going to write this formula. This formula is P critical is pi square EI divided by L square. Okay, this is your N, this is your L. So here, as you know, E is actually Young's modulus, or modulus of elasticity. I, least moment of inertia, least moment of inertia, and L is the original length. L is the original length of the column. Original length of the column. So basically this is the beginning, the length at the beginning of the load you applied. So I'm going to solve a problem from the example, and this is example 13.1. Example example 13.1, example from the book, and the page number, I believe, yeah, page number is 669. Okay. So this is the problem here. So as you see that this is the column, it's a 12-feet column, and the column cross section, if you cut here at this center, you see the cross section is H or I. So basically this is the web flange, and now this is a W type section, and is a W831. So it says determine the largest this member shown in figure is to be used as a pin connected column. Determine the largest axial load it can support before it either begins to buckle or the steel yields. Okay, so since it mentions W831, we need to go the appendix B of the book. Remember the appendix B in page 804, we have all the values associated with the W-shape section, wide flange section. So, and in page number 805, you will find the area, depth, width, thickness, flange, width, inertia, section modulus, all the information here. Now, so from here, from this chart, we find the area is 9.13 inch square, and now moment of inertia in x-axis is Ix is equal to 110 inch 4 and Iy equal to 37.1 inch 4. Okay, so I am writing those values. A is a 9.13 inch square, Ix 110 inch 4 to the power 4 371, and Iy is a 371 inch 4. So as I discussed, as I write before, so our formula is the another important piece is though that is remember let me see. So the yield stress of the steel yield stress is 50 ksi. Okay, it is not given, but you can also get this information I think at the back of the book, or just search the yield stress of steel. It's actually 50 ksi. Okay, now so we know the P critical load is pi square EI L square. So, and we know the L here is 12 feet. Okay, so if I plug those values, so 12 feet gonna be 12 into 12. I'm converted to inch. That means 12 into 12 inch. Now let's see pi square. Young's modulus is also given. The Young's modulus E equal to 29 into 10 to the 29 ksi actually, kilopounds per inch square. So pi square 29 10 to the 3 kilo, so 29, so Young's modulus actually, let's forget, the Young's modulus is 29 10 to the 3 ksi, write it clearly, pi square into 29 10 to the 3 ksi per inch square. Then now the next question, which moments of inertia I am going to take, Ix and or Iy. So you need to look at the orientation of the section. So if you look here the orientation of the section in such that your YY section is horizontal. Okay, so we need to take the horizontal section here. So that's why we are going to select the IY as our moment of inertia, and that is 37.1 inch fourth, and L square is equal to L is 12 into 12 inch square. If I calculate it correctly, this is 512 kilopound. So at 512 kilopound, the column, this column is going to buckle. Okay, 512 kilopound. So to avoid buckling, so 512 kilopound. Now, so the critical stress is critical load divided by area. Okay, critical load divided by area, and area is given 512 kip by 9.13 inch 4. That means equal to 56.1 KSI. Remember, I mentioned sigma yield is 50 KSI. So your critical stress is greater than your sigma yield. So that means the specified load, so that means you need to design a column in with such a load that you can avoid the buckling. So to avoid buckling, your sigma critical must be less than sigma yield, right? So let's see. So the largest load it can support the column can support without buckling is, say, P. Now we know the sigma yield is equal to P by A. Okay, so our P is equal to sigma yield, means multiplied A. The sigma yield is 50 KSI, and A is 9.13 inch square, 456. So P is 456, and P critical is 512 kip. That means when you, for this particular column, your P, you can go 445.6 kilopound. Okay. You cannot go more than that. If you can get more than that, then there is a risk that you can hit the P critical, which causes this column to buckle. But actually, in principle, in reality, actually, you are not going to use this 456 kilopound. You have to add a safety factor. Say the design load would be P design, going to be your P divided by a safety factor, and for example, it's a 456, say it's 1.5, so it will be, let me calculate this one, 456 divided 1.5. If you add a safety factor, so .304, your design force is going to be 304. So this is the problem. Please practice that problem, and it's a very important concept also, because there is a lot of applications of column in engineering, especially the structural engineering. So if you want to know more about this structural column on the buckling, please read this chapter. It's very easy to read. It's not that difficult. So if you have any problem to understand that chapter, you can reach me. No matter you graduate, it doesn't matter you completed the course or not. You are welcome to discuss any topics from this book and any topics in the mechanics of materials with me. So thank you very much for your time and patience, and please watch this video. Thank you.